Okay, good afternoon, everyone, and welcome to another one of our ISC webinars. We are in our final month of webinars. So November will be the last month that will be hosting any ISC webinars. So we are coming to the almost the final leg of the International Space Challenge for 2022. So today we have a very special two-part webinar hosted by Maxa Technologies, with today being the first session and the second session taking place next Wednesday on 17th November. And today Maxa will be sharing with us a little bit more about remote sensing applications and geospatial analysis, which could be extremely useful to teams who are working to analyze space weather data to see how space weather has an effect on our planet. Using satellite imagery. But before we dive into that, as usual, we'll do some quick housekeeping rules. As usual, the chat is free for all to post, to converse, but do try to keep your questions in the Q&A box instead, so that we are able to track all your questions and not miss out on anybody's questions if you have any. So do use the Q&A box for that. We will try to address the questions. We will address the questions at the end of the session. But feel free to post them at any point during the webinar. As usual, the session is being recorded, and for all ISC 2022 participants, you will have access to the webinar via our learning platform, Space Faculty, which will be uploaded in the following week of the webinar, so from next week onwards. And it will be accessible to you until the end of the ISC 2022 challenge. Today's webinar is very interesting because it actually gives you a chance, the teams, this chance to win the Maxa award. So this webinar will hopefully give you some background on what it's like to use satellite imagery and satellite data for different applications and users, and see how you can incorporate that into your projects to stand a chance to win the Maxa award, which is a special award on top of the existing awards that we have for ISC 2022. So of course, if any point of questions regarding so do keep a keen ear out to what our presenter today, Bosco Fong, has to share with all of you. And without further ado, I won't take up too much time. I'll hand the time over to Bosco.
Thank you, Jiren. Let me share my screen. Can you see my screen? Just to double confirm.
Yes.
Okay. Yeah. Okay. So let me get started. So afternoon, everyone. My name is Bosco, Sales Engineer from Maxa. So thank you so much for joining the webinar. So the topic for today's webinar is the intro to apply the remote sensing and also the geospatial analysis. So I hope by the end of this session, so you will have some ideas on how Maxa high resolution satellite imagery can be used in your project. Okay. So this is the agenda for my presentation. So I will start with the very quick overview of who is Maxa, and followed by the Maxa satellite imagery, and also the use cases and insights. So the last one is the Q&A. Okay, so let me start with the very quick introduction on who is Maxa. Maxa is the space technology company headquartered in Westminster, Colorado, United States. So we are specializing in manufacturing communication, Earth observation, and also on-orbiting service satellite. So also include the satellite products and related services like the ground system and the space of robotic arm. So at Maxa, we provide high-resolution satellite imagery. So also include the 3D geospatial data. We also provide the data modeling and the analytic for satellite imagery, as well as we construct the Earth observation and also the communication satellite. So Maxa is industry pioneer and also the market leader. So these are all demonstrated by the following point. So the first one is the resolution. So we provide a very high resolution, 30 to, this is the native 30 to 50 centimeter high resolution satellite imagery. So this the imagery we provide to the commercial market, as well as the defense intelligence industry as well. So so this high resolution is actually able to enable you to see the object that is invisible to other lower resolution satellite imagery. The second one is the geolocational accuracy. So we have the very good geolocational accuracy. So our imagery is able to achieve 3 to 5 meters CE90. So this is the actual geographic location of the object on the ground compared to the position of the object in the satellite imagery. And the next one is our tasking capacity. So currently we have 4 high resolution optical satellite in the orbit. So we're collecting about 3 million square kilometer of imagery daily. So there's about 10 times of Philippines landmass. The last one is our historical data. So we accumulate more than 110 petabyte of the satellite imagery data in our cloud-based archive. So there's about 21 years of data since 2000 until now. So this is very valuable historical data that can be used for change analysis. So let us start with what is remote sensing. So if you are using, if you are reading this sentence, right? So actually you are doing the remote sensing. So in fact, any information acquired from the object without touching on it, so there is the remote sensing. But in scientific definition of remote sensing, so this is the the science to acquire the information about the object or the area. So from the distance using instrument. So usually, in remote sensing industry, so we are using drone and maybe the aircraft to acquire or to capture the data. And so this is for the drone and aircraft. So we also use satellite to acquire, to capture, to obtain the images or the information. So there are many type of satellite out there. So maybe you all heard about the communication, weather satellite, navigation, or EO satellite. So these are the some of the classification, the classes, the category, different category. So the first one is communication satellite. So this is actually used for broadcasting, broadcast television, internet, and also to enable the telephone application. So the next one is the weather satellite. So this is to record and to monitor the Earth climate. So for example, record the surface temperature or the temperature on the Earth. So also include the for example the pollution and also the cloud cover or maybe the cloud cover movement. The next one is the navigation satellite. So this is so for example, we are using the GPS service. So actually you are connecting the GPS. So you are getting the signal from the GPS satellite. So for navigation satellite, so this is more to provide you the navigation to navigate and also the geography location. For example, so you are driving a car, you are using the GPS. So this is under the navigation satellite. So EO satellite, so this is the under the Earth observation satellite. So this is the one that we'll be discussing later. So EO satellite is mainly used for observe the Earth and also using various kind of sensors. So for example, include the optical and also the radar camera. So typically, the EO satellite is to used for the monitor the environment and also used for mapping purpose. So for example, I would like to create a map. So usually they will cover under the Earth observation satellite. So we are taking the picture and also the very high resolution satellite imageries under this part. So in the remote sensing, there are actually typically there are two types of remote sensing: passive and also active. So MEXA current satellites are classified under the passive remote sensing. So MEXA is under this part, optical remote sensing. Okay, so this is the remote sensing system which measure the energy naturally reflected from the ground, so from the terrain. So the sun is as a source of the energy. Okay, so we're using this kind of technique, the system. And the second one is active remote sensing. So for active remote sensing, so this is the remote sensing method that provide their own source of the electromagnetic radiation to illuminate the terrain, and they will collect the signal back. So this is under the active remote sensing. So for example, the radar is one of the example. So there are three types of resolution in remote sensing also. So we need to just have to understand remote sensing. So when they say resolution, so we actually have three different resolution. So first one is the spatial resolution. So for spatial resolution, so this is actually referring to how big the pixel. I mean, when you capture the image, so there's the pixel size on the image. So we need to understand. So this is referring to how big the pixel size, and also how far you can zoom in into the image. And also I give an example here. So this is the comparison between Maxa 30 centimeter and versus the Landsat 15 meter. So this is in meter. So when I zoom in, so this is what you get. So for Maxa 30 centimeter, when you zoom in, you're able to get a very clear image. So this is up to 30 centimeter pixel size. And while for the Landsat 15 meter, 15 meter. So this is what you get because they do not have this kind of information when you zoom in, so you can't get anything. Second one is the spectral resolution. So for spectral resolution, so this is the range of spectrum that the sensor can interpret. So for example, how many bands the sensor can collect. So it's under this spectral information. So for example, in Maxa, so we have WB2. So just to give you an example, WB2, we are able to capture 8 band. So for example, these are the bands, the spectrum that we are able to capture from our WB2 sensor. So this is an example of the picture collected under the WB2 satellite. So we have 8 bands, 8 different spectrum information we are able to capture using our sensor. The next resolution, so this is the temporal resolution. So this is actually talking about the revisit time. So for example, satellite. So satellite capture the image over the area. So when is the when will be the next revisit time? So for example, maybe every 3 to 4 days, or maybe every weeks, and sometimes even monthly collection. So this is actually depends on the orbit at the satellite. So for example, our satellite, Maxa satellite, that one is about 3 to 4 days. So we were able to capture over the same area. So next one, I will show you how the satellite collect the images. So this is the video clip. So actually we have 3. So this is an example will be 3 collection scenario. We have 3 different collection modes under the large area, multiple point, and also the long strip. So this is the video clip show you how to satellite collect the data. This is the multiple point target collections. Yep. So next one, back to Maxa core imagery products. So in Maxa, so we're able to provide the very high resolution satellite imagery. So as compared to other satellite imagery provider in the market. So on this screen, so you're able to see there are actually 5 images. So these 5 images is actually to demonstrate the capability of our resolution. So what detail and what kind of information you can get from Maxa imagery when compared to other lower resolution. So for example, this is our native resolution, 30 centimeter. We also able to provide 15 meter HD. So HD is using our algorithms to reconstruct the images to make the imagery clear. So more information that we can get from the images. Okay, so with the clear information from the images, definitely this will help you to extract and more information, and also precise information that for your specific use cases scenario. So next one, this is the native versus the 15 centimeter HD. So as I mentioned just now, so HD is the high definition technology that we are using. So this technology is actually developed by our, by Maxa HQ. So it's our proprietary algorithms owned by Maxa. So these algorithms, the main purpose is to increase the number of pixels, to improve the visual clarity, and also to reduce the pixelation. So this is the result. So after we apply the HD technology. So it's very obvious, you can see on the roof. So this is the texture on the roof. And also this is the helipad. Yeah, compared to the original 30 centimeter native. And also some of the features along the route. And also the car is actually very sharp compared to the original. after we apply the HD. This is more to post processing power, the algorithms, and this is the original. Okay, so beside the resolution, we also provide multi-spectral bands. So as I mentioned just now, the second resolution, the spatial, after the spatial, so we have the spectral resolution. So as you can see from this table, so actually all our sensor is able to provide at least 4-band multispectral information that include blue, green, red, and also near infrared, except WB1. So WB1 is only able to deliver panchromatic. Panchromatic means black and white. So only WB1 panchromatic. The rest we are able to deliver at least 4-band multispectra. So for WB2 and WB3, we have another additional band that's called a coastal blue, yellow, red edge, and also near infrared 2. So in total, for WB2 and WB3, we're able to deliver 8 band. And also to those interested in the mineral mapping or maybe the mining industry. So short infrared is actually another option. So this under this short infrared, we have another 8 bands. So in total for WB3, we're able to deliver 16 band under the WB3 sensor. So more bands is actually equal to more information because you have more multispectral band. So when you process, you can use up together all this information for your analysis purpose. So next one, I'll give some example for multispectral spectral band. So this will enable you to extract some valuable information, also the insight that you're not able to see. So it's actually to discover the hidden information from the image. So like some example here. So first one is the bathymetry mapping. So this is to measure the water depth. So we are using the coastal blue multispectral band because coastal blue is able to penetrate the clear water up to 30 meter. Second one, this is we are using multispectral for the land use land cover mapping. So you can see we're able to differentiate and classify the land use land cover. The next one, this is for the vegetation analysis, vegetation health. So you can see we're able to extract all the vegetation and do the analysis to estimate the vegetation health. Next one is this the magnetic feature. So we extract the magnetic features. So from this picture, so you can see all the green color. This is actually the magnetic. So versus the non-magnetic object. Also, we are using the multispectral for soil mapping. So you can see all the red colors. This is the soil that we highlighted. So we extracted using the multispectral band. So the other example here. So this is for the water turbidity mapping, the analysis. So we are measuring the water turbidity level using the multispectral band. So these are some of the examples. So there are more, application using multispectral. So next one, I would like to show you the MEXA constellation. So this is the MEXA optical constellation. So just like I mentioned, so we have 2 types of remote sensing, passive and also active. So this is the optical satellite. So we operate the most sophisticated Earth imaging or maybe the optical constellation. So we collect more than 3 million square kilometers, as I mentioned just now, every day. So so from here, so our constellation, so you're able to see, so from 1999 until now, we have total 7 satellites. So let's take a look at the first 3 satellites. So from the Iconos, Kuiper, and also WorldView 4. So these 3 satellites is already decommissioned, retired, so no longer collecting new images. But all the available historical data that we are still able to deliver. So because some customer or some researcher, they would like to have the older data for analysis purpose, especially the change detection. So the other 4 satellites, so this is the on-orbit satellite. So now we have currently is in the orbit, actively collecting the images. So from 2007 until now, so these are the satellite that we have. So the resolution, when you look at the resolution, is actually from 0.3 to 0.5 range. And also the not forgotten the accuracy. So we are improving the accuracy. So the latest satellite we have for the accuracy is about 3 meters CE90. So this is the accuracy. So the exciting news is so our new satellite are in production now. So this is under the World Legion program. So we'll be launching the World Legion satellite in the future. Okay, so this is another example, high resolution satellite imagery. So as you can see, this overseas China, the location is the Forbidden City of China. So satellite imagery is not just the picture. So you may try to think what information or what kind of information you can get from the satellite imagery. So maybe I just try to zoom in further. So this is the native resolution of 30 centimeter. So from this image, actually you can see there's a people. So this is the human, the people. So it's very a group of people here, and also this is actually the frozen water. So these images was taken during the winter season. So more information you can get from the imagery. So for example, we are using the satellite imagery to extract and also to detect some of the smaller features. So for example, around the route, so we're able to get the information like where's the traffic light, the crosswalk, the individual tree, and also the for example the median, the plants, the pavement, and also be able to measure the distance. For example, this one we are using satellite imagery to measure the distance, and also we can use the satellite imagery to do the planning. So next one, we use satellite image, satellite to observe. I mean, as an observer, to monitor the activity of the ground. So for example, this one we are using satellite imagery to monitor the progress. So the work construction progress. So we'll be able to see all the, all the information of the object. So this is the cement mixture, and also the trench. So we're able to get this kind of information to monitor the progress. So now, because with the improvement of the supercomputing power, so for example, now a lot of people they are using cloud computing. For example, AWS EC2, the cloud computing. So and also because of this kind of technology, now we're able to extract more information and faster. So using the high resolution satellite imagery. So what's the example technology and also method we are using? We are using the AI and so the artificial intelligence and also the machine learning method to extract the information. So this is already widely used in this industry. So for example, some of the objects that we able to extract. So for example, I want to extract all the buildings. So we can use the AI and ML technology to get those all this kind of information. And to recognize the oil tank, this example use case using the satellite imagery to recognize the oil tank. Second one is to extract the tree. So this is the individual tree extraction. And the next one is the car counting. This for the vessel detection, aircraft detection. This is the wind turbine and also the high voltage tower detection. So this is mainly for the object recognition and detection. So using AI and machine learning kind of technology. These are only part of it. So there are more, similar use cases. Okay, so for car counting, so this, for example, this is the example use case. Once you extract the car, so what's the use cases? So what's the example use cases that we can use for this kind of information? So for example, we have two images here. The first one, the images are based on the car counting. So we extracted about 175 cars on the route, and the second one, so this is 2009. So few months after. So another detection. So we are using the images to calculate number of cars. So this kind of information, so some company they are thinking to use this kind of information. So for example, now I'm able to monitor the traffic flow. Okay, so for this kind of information, so they can help them to, for example, for the road maintenance. So maybe they're now trying to get this kind of information and for their road maintenance. Okay, so for next one, the land reclamation monitoring. So this is another use cases using MEXA high resolution satellite imagery. This is mainly for the progress monitoring. Okay, so the area here, so this is the Hong Kong International Airport. maybe some of you or maybe is able to recognize this area. So this is the Hong Kong International Airport, the third runway. So they're trying to build the third runway. So we are using the high resolution satellite imagery to monitor the progress. The total square kilometer of this area, this is the third runway. So there's about 6.5 square kilometer. Okay, so through the high resolution satellite imagery, for example, I point out a few areas. So this is to, to understand what kind of activity and what they are doing and the progress. So in area highlighted in number 1, so this is the vessel with the marine sand loaded. So we can get all this kind of information. It's very detailed. And the second one is the sand dredging and unloading the sand. We also able to see the smaller object, the excavator, sand discharge activity, and also the sand discharge vessel. Okay, so next one, we are doing some analysis on our images that we collected over the Hong Kong International Airport, the third runway. So the first images, this was taken on the October 2019. This is movie 1. So just as I mentioned, movie 1 imagery is actually black and white. So this is the example black and white imagery. So based on the calculation, so this is actually 31% completion. And second one, this is the we're using the movie 2. So the images was taken on 2020 January. So based on the calculation, this is about 49% completion. And also in February, so this other imagery, so it is about 51% completion. And this the another one in March, so 55%. So so we brought this information into a graph. So now you're able to see this actually, the reclamation progress. So in based on the last images, the total area is about 3.59. So just as I mentioned, the total area is about 6.5 square kilometer. So in March 2020, it's already 3.58. So, and also we are able to measure and vectorize to digitize and vectorize the total area that we calculated from a satellite imagery. So this is the extended area, so we can see how the reclamation progress. So different color is represent different the total area get from different imagery. Okay, so next example use case, this applied to forest application. So for example, for the forest activity. So why we are using high resolution for most of the scenario? So for example, this is 3-meter resolution. And what information can we get or can we extract from this low resolution? So when we look at these images, so we know something are there, but we cannot confirm. Okay, so when we try to zoom in, so you get pixelated, so we can't see, we can't confirm, and also cannot see, we get all the information. So when I switch to the MEXA 30 centimeter imagery, so this is the high resolution, so we can see now so this area is actually buildings, and also the buildings here, the car park, and also we are able to calculate number of car, and also we are able to see the canopy, the tree canopy. So that's why the high resolution is very important to detect and also to tell you what is actually happening on the ground. Okay, so next one, this is the by visual interpretation. So just use the imagery to view. And so from the high resolution imagery, you already are able to get some basic information. So for example, this area is actually the palm plantation, natural forest, and also this could be illegal logging. So when I switch to the multispectra, so I try to embroider the multispectra. So this is the 8-band again. So I'm using the near infrared 2, red edge, and also red band, the band combination. So this is the example of using multispectra. So the gray area, so this is actually the clear cut. So now it's very obvious when we use the multispectra band. So next one, this is an example of false color. So we are using 8-band. Again, I'm using the near infrared 2, red edge, and also red color. So this is the combination. And what kind of information you can get? So it's actually very obvious, be able to differentiate the man-made and also the natural vegetation, and also the agriculture area. So, and also some of the, for example, the man features and for example, buildings, and also, for example, the road, we also to be able to detect using this multispectral imagery. So another advanced analysis applied to forest. So for example, I'm using satellite imagery, especially the multispectra. So I'm able to get the forest canopy density. So these two images actually natural color. So once I apply the density mapping, so this is the result. So I have two images pre and post, and this is the density level. So you will notice the high density area is actually reducing. So this is the result. So the high density level is actually reducing about 2.35 square kilometer. Yeah, so we can get this kind of information from the satellite. Okay, so another use case here. So using Maxa high resolution satellite imagery as a foundation to update the Uganda map. So this is the project that we are doing. So the update map is actually for the chimpanzee habitat and also forest protection and restoration program. So we apply the persistent change analysis. So the change analysis is actually to locate of the persistent change area. So this will help us to focus on the area that we want only the change happen. So from the map, so you're able to see there are green color and also some of the yellow color. So the green color, so this is the added wooded area, and the yellow color, so this is the root. Okay, so from this kind of information, the latest updated map. So this information we will provide to the some of the related department. So they're able to have a better understanding to understand where are the human footprint, and also to inform and measure the success of the ongoing tree planting, and also the forest restoration and the protection effort. So from the picture, you're able to see they're actually using Maxa imagery. So as a base, you can see the logo here. So they are digitizing and also the delineate the information from satellite imagery. Okay, so next example use case. So this one is for the wildfire. So again, just now I mentioned WB3, we're able to deliver the short-wave infrared. So this one, this application, we are using short-wave infrared. So why we are using short infrared for wildfire? So this is because the short-wave infrared are able to penetrate the smoke and also sensitive to the thermal emission. So because and also are able to to detect the active fire. So based on this kind of characteristics, so we are able to use the solar infrared for wildfire application. So example here, so the first image, so this is the image natural color. So this is what you see. So when fire happens, so it's always covered by the smoke. And when we switch to the solar infrared, so this is what you can see. So we're able to see, to get the information on the ground, and also able to detect where are the active fire. So for example, this one, so this is the high thermal band, the high temperature area. So we can detect, so this is the active fire, and also able to differentiate the burnt area and unburned area. So this kind of information is actually very helpful to support the firefighter to plan their approach. So next one, so this one we are combined with the building footprint and also the natural color and the solar infrared. So for example, the first one we're using natural color to extract all the building footprint, and second we are using the solar infrared to detect where are the hotspot, and we intersect. So we know that. So based on this kind of information, roughly we're able to calculate and estimate the total number of buildings that are affected or within the hot map. Okay, so next one, this is applied satellite imagery for the post-disaster assessment. So on 28th September 2018, so I believe you may aware this disaster. So this is the Sulawesi earthquake, and the tsunami happened 2018. So some images taken after the tsunami happened. So this showing the damage level. So for example, this one, so we're able to see the bridge has been destroyed. So after the tsunami, and also you're able to see there's a lot of damage. And we are doing some comparison using the pre and post event. So this is actually this is a previous saw line, so extended. Yeah, so this before and this after the tsunami happened. So also from this disaster, so we can see that so this area is actually soil liquefaction happened in this area. And this one we are using the geospatial information. So for example, the combination of the satellite data and also the all the GIS layer. So the GIS layer that we are using consists of the road network and also the buildings. So for example, this one, the road network. So we intersect and also to estimate, the damage level. So for example, those highlighted in the orange color. So this is actually destroyed. So this part is destroyed, this area. And also the second one, this is the yellow one. So this is the damage and also the possible damage. So we can classify into a few classes. And similar to the building, so this is the post damage assessment. So we're using the building and combined with the satellite imagery. So classify into 3 classes. So partial damage, destroy, and also total damage. So based on this kind of analysis, the government or maybe the local government, they're able to get, the roughly the damage level after the disaster happened. Okay, so next one, for the water turbidity analysis. So this one again, we are using multi-spectra information. Okay, so the water turbidity measurement here, so we are utilizing the multispectral band information from our satellite. So because the clear water will have highest reflectance in blue color, the blue color bands, and also of the other visible spectrum. So and they are also the high absorption in the near infrared. So because we can use the near infrared band and also the blue bands for this kind of analysis. So this is the example analysis that we are using, the multispectra. And from this image, this result, you can see that. So the red color, the dark red color, is actually the high turbid level. And those are in light blue. So this is clear water. Okay. So next one, we apply the water turbidity analysis to the river. So this is the first image that we use. This one was taken on the 2018, April 14. So this is the analysis. So the turbid level is very low. Okay, so this is in blue color. And the next images, so after a year, so this is another example. So we apply the turbidity level analysis. So you will notice the water turbidity level is actually increased. So now this is turned into green color. And you will realize this area, so it's a bit, a significant change in the turbidity level. So this is actually because we realize that this is actually the wastewater treatment plant. So actually to release this, so they release the treated water into the river. So that's why you're able to see there's significant change in this area. Okay, so next one, apply the satellite imagery for agriculture mapping and analysis. Okay, so the screenshot here, so this is the Maxa Secure Watch platform. So this is our platform. So I just wanted to show you the false color satellite imagery. So this example, we are using the near infrared 2, yellow, and also closer blue band. So this is the band combination that we are using to display and also to differentiate and get to highlight the vegetation. So the near infrared spectra response from the vegetation is very unique. So like what you see here, so all the red color, so this is represent the vegetation. Okay, so this is because the healthy vegetation will reflect the infrared light very strong. So and also this type of the false color images so can help to do a further analysis of the vegetation. So for example, I want to know the whether my vegetation is healthy or not. So the plant and also the plant stress and also the crop types of the the mapping. So for example, this one we're using ICBAN multi-spectral band for the crop classification. So this is the example. So based on the multispectra, so we're able to classify into few classes. So just using the multispectra. So for example, if let's say you have some Gauss-Truth information, or maybe the spectral signature, so you're able to classify more classes and get more precise classification result. So on the other side, so this is the natural color image again. So if let's say I want to know whether my vegetation or the plantation area, whether is it healthy or not healthy. So whether this kind of natural color image is able to tell you or not, but definitely I think it's very difficult. So now I try to apply the vegetation analysis. This is called the NDVI. It's actually the normalized different vegetation index. So just use the near-infrared bands and do some analysis. So based on this calculation, this is actually the calculation is depends on the chlorophyll, the absorption from the vegetation. So it's based on the chlorophyll content. So from this analysis, the vegetation over the darker area. So for example, this one, the purple color. So this is actually very stressed. So meaning the unhealthy vegetation area. And those are in red color. So this is healthy because the chlorophyll content is higher compared to the other area. So this kind of information is very good for example, fertilizer, fertilization application, irrigation for water supply, and also as well as the crop yield production prediction. Okay, so next one, this is applied to, so we're using multispectra for the tree health monitoring. Okay, again, we're using multispectra band. So this applied to the individual tree. So based on the research, so there are three internal warning indicator from satellite data, which correlate to the leaf chlorophyll content. So the first one is drop in the near infrared reflectance. Second one is the red edge. So this also drop in red edge reflectance, and the last one, this is drop in red band absorption. So if let's say combine everything, all these three occur, so meaning the structure of the tree is unstable, and also there's a risk of collapse. So this is the example, the stress versus the healthy vegetation. So from the graph, this is the spectral reflectance from the tree. So by comparing these two, so you know that, so actually for stress tree, so the reflectance from the near infrared and also the red edge will be lower compared to healthy trees. And also the other one is the red edge, the red spectrum. So these 3 points we need to, we can use for detect whether the tree is healthy or not. Okay, so we apply this kind of analysis to the tree. So so this one is the example. There's the tree collapse incident. So this is actually the heritage tree. So it's more than 270 years old. Collapse in February 11, 2017. So based on the spectral analysis, so this is the result. So we extract the historical imagery and then we do the analysis. So we realize that actually start from 2010 and also 2015 and also 2016. So actually the near infrared reflectance from the tree is actually dropping. Okay, so this is one of the warning sign. So end up this tree was collapsed in 2017. Okay, so this is the last use cases. So this is for the urban vegetation to reduce the urban heat island effect. So as you may aware, so city area usually will have a few degrees warmer compared to the surrounding rural area. So this is because of the remove of the natural land cover and introduce the urban material. So so urban heat islands so may contribute to the climate change. So because by increasing the demand of the air conditioning during the heat wave. So so we are using satellite imagery to detect and to measure the vegetation coverage over the city area. So this one we are using Worldview satellite to estimate and also to extract the vegetation coverage. So this is an example of the result. So we're using multispectral band, and this is the when we zoom in, so you can see so the vegetation extracted is actually very precise for each pixel. So again, we applied to a number of images from 2018, 19, and also 2020. So this is the Xiamen Island. So from the first images, based on our calculation, the green area, so it actually is about 46%. And 2019, so this is 44%. So it's dropped a little bit. And in 2020, so this increased to 49%. I mean the vegetation coverage over the Xiamen Island. Okay, so well, I think this brings me to the end of my presentation. So before I proceed to Q&A, so I just would like to let you know that we actually prepared 3 sets of sample data. So over the these 3 areas, so they include the Singapore area. This is the Philippines and also India. So we selected 3 areas. And the total area for Singapore sample, so this is 79 square kilometer, 125. So this include the sea area, and also the for India, so this is 62 square kilometer. And so for our MEXA sample data, so we arrange 2 type of products. So they include 4 bands and also 8 band bundle. So we can try and experience to use 8 band for your analysis or maybe for your project. Okay, so these 3 sample data sets, so we will give 3 different images. So from so we selected 3 image, so they are from different year for each set of the sample. So I think now you can start request and send the the information to Jiren to request the sample data. So I think when you request the sample data, so these are the information you need to provide. So this is just for us to record, also for our records purpose. Okay, so last one. So I think so just to let you know that, so we will have a follow-on workshop. So just now Julian already mentioned on the next Wednesday. So I will be sharing the unlocking insight from satellite imagery, and I also will demonstrate how to process and extract information from our multispectral data. Okay, so please do register and join us. Okay, thanks.
Thank you, Bosco. Okay, so we'll jump into Q&A. Thank you for that session. It was very insightful, and I think we've gotten quite a number of questions from the audience. So the first question, which was anonymous, which I believe Mary already answered, but just so that everyone was aware, someone asked, what orbit do MEXA satellites use? As Mary responded, they primarily use sun-synchronous. The current satellites use sun-synchronous orbit. If you remember if you were attending our orbital mechanics webinar a couple of weeks ago, you would know that some of the advantages of sun-synchronous orbit includes that the images are always in constant lighting, and it covers the entire globe. So you can basically get images from any point in the globe at periodic intervals. The second question, the next 2 questions are from Miat No. The first one being, how can satellites be used to observe ionospheric responses to space weather? How does the system work? And what are the technicalities and logistics? So this is not really a remote sensing question. This is probably more of a, how can satellite data be used to observe space weather? So what we're trying to share with you here through MEXA sharing is that there are more than one ways to find data regarding solar flares and radiation that may not necessarily be direct. Because obviously if everybody does the direct method of trying to measure solar flares using a radiation radar or anything like that, you're all pretty much going to have similar projects. So what we're trying to offer you here is alternative means to tracking space weather data by using your problem-solving skills and inference skills to infer results from the data that you see that MEXA is sharing, very kindly sharing with all of you. So I thought a very good example was Bosco sharing about the wildfires. So wildfires, obviously, we know is an effect of climate change. And this climate change could be a result of, if you are comparing it to old space weather data, if you're comparing to old space weather data, this can be used to see if there is a tie between the increase in solar flares and an increase in climate weather in the weather in area that could result in wildfires. So that's one of the ways that you can maybe think about it a bit more abstractly, and then this helps to give you an additional creative stance to support your data or your findings in your projects. I don't know if Bosco or Mary might like to add on to that part.
No.
Otherwise, so Stephen asked, what software are used for imagery or image processing of the satellite? Can a mid-range gaming computer handle such high data processing as well as ML extraction? I think he had a follow-up question, which is, was Secure Watch an open source software? And he sincerely really likes the remote sensing technology and would like to explore more about it.
So this one I can try to answer. So the remote sensing software that in the market, so usually we are using PCI Geomatica. So in the next section, so I will share, to give you the list of the remote sensing that we are using in this industry. So I can give you an example. So the open source one, so you can try to explore a little bit more on the QGIS. So there's open source. I think it's quite powerful to manage all the vector data. And for the image processing, so you can try. So there's some limitation. So because for remote sensing software processing, to process the imagery. So basically there are three. Just I mentioned PCI. Second one is the NV. And we also use the ADAS imaging. So these are the common three image processing software for remote sensing industry. So with a gaming, laptop. So usually we recommend to use a workstation, but I think the gaming spec now is already good enough to process the satellite imagery. So to be honest, I'm just using the Core i5 7th generation kind of a laptop to just process a very small area. So just now, Peter, I'm not sure you noticed the total file size of our satellite imagery is actually very huge. So for example, the Singapore data set. So this one is just the 79 square kilometer. So inside we have two set of products, 4-band pen sharp and also 8-band bundle. So roughly, I think if let's say you're processing maybe just the 8-band bundle, so this will be lighter because the 8-band bundle, the resolution, this is before pen sharp. So the file size will be smaller compared to after pen sharp. I think to handle this kind of, the size of the imagery, you need to have a very powerful GPU and also the CPU. So that's why now in remote sensing industry, we are trying to use cloud computing. So just as I mentioned, EC2 from AWS. Yeah, so a lot of customers, they're switching to the cloud computing power.
Thank you. Hopefully that answers your question. If you have a follow-up question, Stephen, just feel free to post it in the Q&A.
Yeah. The Secure Watch, right? Yeah. Secure Watch is not open. Yeah, Secure Watch is not the open source platform. So that one is our, what's our product.
Yeah. So yeah, Secure Watch is not open source. But interestingly, the award, the MEXA award comes with some usage, a year usage of the Secure Watch software. So if that's something you are really interested in pursuing, this is a great opportunity to get some experience in remote sensing and geospatial analysis. And then hopefully, if you stand a chance to win the MEXA award, that will also give you access to the Secure Watch platform for, I believe, 12 months, if I'm not wrong, if the information is correct. Carl has a question. Is satellite imagery limited to just tangible things, or can we also observe intangible ones like temperature, atmosphere, electrical charge, etc.?
So this one I give one example. So because this is, depends on the multispectral band that the satellite sensor can collect. So right now we are focused on the near infrared only up to short infrared. So for example, if let's say you want to detect the temperature, so you have to use thermal infrared. So thermal infrared, I think Landsat satellite, so they have this sensor to collect. So meaning you can get, some example, satellite data from Landsat. So that is able to help you to calculate the temperature. So because they have a thermal infrared sensor. So for MEXA, we only focus on the optical. So which is just I mentioned, the red, green, blue, and the infrared, and also up to short infrared only.
Thank you, Carl, for that question. Hopefully that helps you formulate some ideas about how you want to work around using this kind of data for your project. Okay, so Mietno has a couple more questions. How do satellite constellations work when it comes to taking Earth data or Earth images, and what does multi-point data arrays work? How does multi-point data arrays work?
I'm not sure whether I fully understand the question. So the second part,
maybe Mietno, if you can elaborate on your question either via
Mhm.
chat or just post out a follow-up question. We'll come back round to that one later on. How do you connect ground data to satellite data, and what exactly does it mean for satellite signals to be distorted? How do you connect ground data? By ground data, do you mean data of Earth? So when we talk about satellite data obviously covers everything, any kind of data that your satellite collects. So in the case of MEXA satellites, for them, satellite data is, I would also assume here, if you're talking about ground data, meaning Earth images, their satellite data is also ground data because their satellites are designed for Earth observation. So Earth observation data, but of course, if you're talking about satellites to monitor purely space weather, you wouldn't get any ground data because your satellite will be carrying a different payload. I don't know what it means. What does it mean for satellite signals to be distorted? Satellite signal distorted could mean a variety of things. It could either mean that there is interference from possibly a solar flare or different reasons for the signal to be interrupted. In the case of some of like Earth observation satellites, satellite signals can be affected if there's too much cloud cover as well, right? So say like your satellite data can be affected if there's too much cloud cover, if you're not using a SAR satellite. So I'm not sure if that answers your question. How frequently do MEXA's image refresh over the same area? I guess not refresh is the correct word, but how frequently does MEXA satellites cover a certain area? What's the period?
Yeah, so this one I believe is the frequency, how frequent we capture the satellite data over the same area. So because MEXA is commercial company, so we actually depends on the demand, the customer demand. So for example, for city area, so usually we will have high demand over the city area. So meaning you will get bonus if let's say your project area is within the urban area. So if let's say for a rural area, so the demand is very low, So so in that area, so maybe one image maybe for a few months. So for example, the whole year, maybe we only have few images, or in some scenarios, so there's nothing. So it actually depends on the demand. And for city like Singapore, of course, we have a lot of images. So for example, maybe every month, so we have one images cover these Singapore. So this is just an example. So and because we optical satellite, so it's really highly depends on the cloud cover and also the weather condition.
Okay, hopefully that answers. I think that will answer your question. Okay, so Mietno elaborated on her question, which is about multi-point data arrays. She said what she meant by multi-point data is how does data from different satellites be interpreted at the same time, especially if they are far away from each other. One probe observing the sun and the other satellite is in low Earth orbit. Is it done manually or computationally? And if so, how does it work logistically?
So this one, let me try to answer. So maybe let's say it's related to remote sensing. If let's say you have multiple source of the satellite data. So for example, I have the maybe WoW satellite, and also you're using some middle resolution, and maybe some you're using another lower resolution as well. For example, NASA. So because we are capturing the reflectance from the Earth surface. So first thing you need to convert, everything into reflectance before you can perform the analysis. So because we need to make it standardized. Mm-hmm.
Yeah. So I think this is, it's usually done manually in the sense that someone needs to input the programming
Yes.
for when the satellite to
Yes.
take the images or to collect the data. So it actually needs, so manually, I would say both manually and computationally, someone needs to think about what time they need to collect the data, and then you put in a code, and then automatically when that time hits on the satellite, then it will collect the data. So it's a combination of both, I would say. With a file size so big, how do we download the imageries? We will actually advise you to download it maybe on a secondary hard drive, or a external hard drive, or maybe even a thumb drive. I know thumb drives can manage quite a lot of data nowadays. Download it onto something, not onto your main computer, obviously, because that might cause your computer to crash. But we will also send over an instructional sheet on how to download the image when you request for them. Yeah. So I think.
So just to make sure you have sufficient the storage. Before you download the images. Yeah, because when you look at here, so for Philippines sample data says up to 43 gigabyte.
Yes, so just make sure you have some way of sufficient space on something to store the data before you try to download it, and then you should be okay. But yes, satellite images have take up like quite a lot of space, but that's something that you would have to try to learn how to work with, which we will go more into in next week's webinar, next Wednesday's webinar. So how do we use interference of space weather with satellite signals for mapping applications? I'm not quite sure what you mean by this question yet, no. Interference of space weather with satellite signals for mapping applications. Are you talking about how to track a space weather is affecting satellite signals? If it is, if you remember from one of our earlier webinars, Professor Gang Kai shared that typically when there is a solar flare, a lot of scientists or satellite operators automatically will shut down their satellites for the period of the solar flare to prevent any severe damage to the electrical systems of the satellite. So usually when you shut down, it just basically means there will be no data available at that point of time. Otherwise, I'm not sure how else they will be able to measure satellite space weather changes. But if this is something you find, you feel free to share with us. I'm pretty sure it will be very helpful for a lot of satellite operators to know how to better manage solar flares and issues like this, so that doesn't interfere with their operations. But with that, and we're just over time, but I think that is the last of our questions. Thank you so much to Bosco and Mary for joining us for this session. As mentioned, we have a follow-up webinar next Wednesday on the 17th at the same time, where Bosco will be sharing more on how to do on satellite imagery processing and analysis. So it will go more into the technical aspects of how to actually process the data that you would have on hand. I'm sharing the webinar link, the registration link in the chat right now. So if you haven't already signed up, do so. And yeah, if at any point of time you have any questions, as usual, please feel free to share it with us. Via email. Bosco and Mary are happy to answer them to answer any questions related to the data or about remote sensing applications or geospatial analysis. So just feel free to send in your questions. And as mentioned, we'll be uploading this webinar onto the learning platform by next week for your reference, so you can look back on it and maybe look more into details about any point that you missed out. Otherwise, thank you everyone for joining us on Friday. Thank you, Stephen, for your questions. we hope you learned a lot. Yeah, and we look forward to seeing you in the rest of our webinars. And hopefully this gives you more insight on how you can stand a chance to win the MEXA award and maybe look into more creative ways to develop your projects. But yes, thank you, everyone.
Okay, thank you.
Thank you, Bosco. Thank you, Mary.
Thank you. Bye-bye. Thank you, Julian.
Thank you, Julian.
Thank you.